Chapter 2 is not on the test. Nope, you can just let all that flow right out of your brain as well, as long as everything we're going to talk about today, which is some weird stuff, really. And we're going to have to deal with waves in a little more detail. And sadly, it would have been nice at this point if at either the end of last semester or the start of this semester, we had sort of a whole block dedicated to waves, because a lot of the fundamentals and stuff would come in handy at this point. But alas, this particular class course doesn't do that. So there may be a few things that I sort of brush over thinking you already understand. And if I do that, by all means, stop me and ask me to back up and re-explain that topic or that concept, okay? So everything that we're doing in Chapter 3 asks us to sort of go back and remember that light is a wave. We considered that fact when we dealt with polarization. That was specifically about the electric field component of the electromagnetic wave that is light in general. When we dealt with all of this stuff about refraction and reflection, we sort of stepped outside of the wave idea and just imagined light being a ray that sort of just travels in one direction. And we didn't consider the fact that there's a wave hiding in there that could do other weird stuff. We just abstracted away from that, and we did what you might call geometric optics. That just deals with the geometry of the way these rays travel, okay? To do Chapter 3 and Chapter 4, we're going to re-enter the concept of light being a wave and look at some other effects that occur specifically because it's a wave. None of this would happen if light were literally just, I don't know, some sort of weird beam that travels from one place to another. If there's not something in there that's a wave, none of this can occur. So first of all waves, whether we're talking about electromagnetic waves or waves in water or waves like on a rope that I'm shaking up and down, any kind of wave anywhere exhibits this property known as superposition. So don't think that this just applies to light. I just need to introduce it because we're going to use this concept over and over in this chapter. Superposition, which means that if I have multiple waves that are traveling through a given area, and we'll say maybe they like pass through each other, they hit each other, they interact with each other in some way, the total or net displacement at any point is just the sum of the individual displacements by all the waves at that point. And I'm going to have to back up a little bit to explain that a little more, okay? The net displacement is the sum of the displacements of all the waves at an individual point. So let's imagine we have just a big pool of water. It's like right up to here. You people are drowning. I'm sorry. The rest of us are good, all right? It's like right at this level. I'm happy. My neck's above it. Like, apparently this is a me-centric sort of level of water, I guess. It's right at my neck, all right? And let's say that maybe over here you drop a rock in the water, right? And it just goes in. And as it goes in, it disrupts the water. And we've all seen this before. There's like ripples that travel out from that point and eventually sort of just die away, okay? What if instead of just dropping the rock, maybe I just take the rock at this point and just sort of go and just shake it up and down? Now you can imagine those same ripples, they're going to sort of keep emanating from that point. Those ripples are what we're calling the displacement, like literally the physical movement of the water up and down around that starting level. That's how much the water has been displaced by the wave, okay? Keep in mind, a wave isn't like taking water from this point and moving it over here. All of the water is staying in the same horizontal location. It's just parts of the water are sort of vibrating up and down. Are you okay with that idea? Yes. Mm-hmm. I'm saying, well, the amount that I'm moving the rock up and down is causing the exact same motion in molecules of water that are displacing this much. So if I move the rock, say, this much above the water and then down into the water by the same amount, and I went over here some distance, I would find molecules of water that are moving up by that amount and moving down by that amount and sort of being displaced from their starting location, which was right in the middle when they were at rest. What are we adding? Okay, we hadn't got there yet, but let's do that. Question first. Two separate cases. So dropping the rock was just to help you remember, like, ripples could happen. Now I'm, like, repeatedly dropping the rock, if you wanted to think about it that way, by physically moving it up and down in the water. It's kind of like we're sloshing in the water, I guess. Mm-hmm. Yeah. Yes. Mm-hmm. Exactly. Yes. Displacement is officially the distance from the middle. So there's like a positive displacement of water and a negative displacement of water. If you know more about waves, it's an amplitude. Okay, it's how much from equilibrium we're talking about. Okay, so when we're talking about adding things together, what if we did that twice? So now I've got like a rock over here and a rock over here in the water. And like maybe you're taking one of them and moving it up and down like this, sort of making the water do that and create waves going this way. And maybe another one of you is over here just going, like you're moving it up and down really fast. So two different waves of two different frequencies. And maybe even at the same time, maybe the person maybe this is a toddler. I don't know why I'm saying, like they're also like doing like this, like making big, huge displacements, okay? You're thinking like, that's not a toddler, that's you, right? One of you, that's exactly how you would do it, all right? So these two waves are going to eventually like travel and hit a point of water like somewhere in between them, okay? And maybe the wave that's going this way has water molecules that are moving up and down this amount. And maybe the ones that are coming this way has water molecules that are moving up and down this amount. When those get together, those displacements add, okay? So if they happen to be at a peak when they get at the same point together, then the total displacement adds and you get like more displacement in the middle. If it just so happens that maybe when they get together, like the big displacement is up, but the littler displacement is down, you can imagine it's going to subtract a little bit. And then there's an infinite number of possibilities in between, where maybe it's not right at a peak in a valley, maybe it's kind of halfway in between. No matter what's happening, the displacements of the waves add. And it doesn't matter how many you have. We could have a whole pool of people, right? That are all bouncing up and down, making waves in different ways. The displacements of the water molecules in the wave at any point is the sum of the displacements by all the waves, okay? An interesting thing about that is they don't really affect each other. Like, the waves sort of just like pass right through, and they add when they hit each other, but they don't like, I guess, kill each other or make each other stop or anything. Like, you could just be over there at the other side of the room, and the wave that started here would pass through this wave and just sort of keep on going until eventually sort of friction knocked it out, okay? Keep this idea of superposition in mind, because I think the next two concepts you've probably heard about. Superposition is the basis for two different types of interference that we're going to deal with a lot. These waves, when they superpose, when they're added together, they're interfering with each other in some way. They're affecting each other. And the result is that they affect each other's displacement. So if I have something known as constructive interference, that is when they run into each other and you have superposition resulting in a higher overall displacement. So it's like two positives are adding together and I get more positive. The two waves hit each other and you end up with more displacement. If it's destructive interference, that's just when the positive displacement of one wave hits the negative displacement of another, and the overall sum is less than what you would have if you add them both together by magnitude. Constructive adds together in a positive manner. Destructive destroys a little bit. You have a little bit less than you would have otherwise. Let's all take a breath. That was good. Some of you actually did. Congratulations. Yeah. The others of you, like, you breathed. You just didn't, like, take a breath, right? You're just, like, casual background breathing. Yeah. Some of you are like, now, he told me to take a breath. I'm not going to do it. I will hold this breath as long as it takes. Okay, don't breathe. And then, okay, now you're good. I don't know what's wrong. Yeah, see? Oh, wow. I hear a lot of breathing out there. So this idea of interference, waves interfering with each other, is the bulk of everything that we do in this chapter, okay? We are going to put some requirements on light that allows us to actually see this interference happening. So let me put a little note here, and let's say that superposition happens without these conditions. But if I want to see those two types of interference right above, constructive and destructive, my light waves have to meet these two requirements. And already, I was thinking like, oh, we've got 13 slides, we'll be done in 30 minutes. I'm halfway through the first slide, this is going to take longer than I thought, which is totally okay, because, hey, we've got time, right? None of this is on the exam Wednesday, we're fine. We'll finish up whatever we don't get to Friday. Requirements. First of all, monochromatic. Monochromatic meaning essentially one color, or think of it as one wavelength or frequency. Whatever sources of light that I'm trying to put together and have them interfere, they must have the same color. And by color, we simply mean either the same frequency or the same wavelength, which is really just one is the same thing as the other. Okay, it's just different ways of looking at the same thing. Remember that the speed of light is equal to lambda, the wavelength, times the frequency. So if I'm going to have a constant c given a certain f, it's going to have a corresponding lambda that goes with it. C is equal to lambda f. So our two sources have to have the same frequency or the same wavelength. The second one of these is a little bit harder to see, and I'm going to need probably 2 slides from now to help clarify a little. Your question. So we want to be able to observe constructive and destructive and interference of light waves. For that to happen, I need to put these requirements on it. However, like if I have 2 sources of light of any type, whether it's that light bulb and this light bulb, which don't meet these 2 requirements, still their waves are interacting in such a way that, well, the wave displacements add and subtract when they hit the same point. That always happens no matter what. I said the 2 opposite things. Superposition, the addition and subtraction of the waves, is going to happen no matter what. To be able to observe the specific case of constructive and destructive interference, I have to have these 2 requirements met. You may not be able to see the distinction between those 2 yet. It might take another slide or 2 for it to come out, but let's see what happens. Okay? Coherent. Sources that are interfering with each other have to have a constant phase relationship. What in the world is a phase relationship? Well, let me just jump ahead 2 slides. Is that okay? I want to show you a couple of pictures instead of drawing them myself because they're just going to look nicer here than they would otherwise. Let's take a look at the top left. Notice they have a nice plus right there in between. These are 2 different sources of light waves that we're adding together. Okay? Notice in this particular case, when one of these peaks at the exact same time, the other one peaks. And when this one peaks at the exact same time, the other one peaks. First of all, these 2 have exactly the same wavelength and frequency. So they meet the first rule, so that's not a problem at all. But also, they're staying what we would call as in phase with each other. By phase, we mean, are the peaks and valleys matching up at exactly the same time, or are they not? Okay? So here, they are perfectly matching up with each other. Notice if I go down below, they describe this as in phase. We could say that they have a constant phase relationship because they stay in phase. As time goes by, this idea of them peaking at the same time and valleying, to coin a word, I guess, at the same time, never changes. All throughout time, that relationship stays constant. So you might think, Like, well, how could I ever really have something else that would still maintain a constant phase relationship? Your question? A constant period for each wave? Yes. So by period being the same, they have to have the same frequency. All of that would have to be the same for them to stay in phase like this. Yes. What if one of these waves started a little later? Okay, think about like just taking, I don't know. Well, let's just go straight over to this other example. Here I have two waves. Notice they don't peak and valley at the same time, right? This one is at a peak while this one is at a valley. And then this one is at a valley while this one is at a peak. And then this one's at a peak while this one's at a valley. Okay, they're not doing the same thing at the same time, but they're still maintaining a constant relationship. The difference between them is staying exactly the same. In other words, I could go all throughout time, and every single time the top one peaks, the bottom one valleys. Every single time this happens. So they're not in phase with each other, but they still have a constant relationship, a constant phase relationship. It just so happens they're not in sync with each other in the same way that the first one was. In the first case, in phase meant that the exact same thing was happening at the exact same time. Now they're doing different things at different times, but they always do the same different things at different times. Was that a confusing sentence or not? Maybe a little bit. Every time one peaks, the other one valleys. Always. That never changes, which means I can still say that their relationship is constant. Both of these cases meet the case of them having a coherency. The two sources are coherent. Go back 2 slides. Notice I just need a constant phase relationship, whatever that happens to be. And it doesn't have to be one of these two cases either. What if instead of, I can't draw this. What if instead of one peaking at the same time the other one valleys? What if maybe every time one's at a peak, the other one is just coming down from the peak? Okay, like they're shifted just a little bit different from each other. That would still be a constant relationship as long as every time one peaks, the other one is just coming down the peak a little bit. As long as every time that happens, it's exactly the same, that's still a constant phase relationship. Do you understand what I mean by coherent at this point? I see a few nods. I see a few nods. Maybe you're kind of holding it together a little bit. Maybe your brain is leaking because of all the work you did this weekend trying to prepare for the exam. I understand. It's okay. We'll revisit this stuff later as much as we need to, okay? Monochromatic and coherent. So, we've got two very made-up sort of waves here that really don't represent much of anything, okay? Wave A and wave B. If I superpose them, if I add them, which one of the bottom 4 options would you get? Your question. I don't know if I can. Oh, look at that, I did. Yes. Forward. This one, yes. It looks a whole lot like the first one, right? Yeah, it is exactly the same. Why describe it as something new? There's really no need to. Yeah, it's kind of useless in a way. But I'll mathematically show you what that means in a second. Okay? Well, that A and B, they really went all out, didn't they? I don't think we've had A and B labeled in such a fancy, shadowed, bold way before. A little bit ridiculous. Add those two together, and what do you get? You're voting something there. I can't see it. I see a lot of 3s. Does 3 sound good? 3, 4? How about 4? No? 2? 3 looks pretty good. Basically just merge these things and see what happens. I have to have this bump, which adds to nothing, so you're just going to have that bump. And then I have this bump, which adds to nothing, so you have those 2 bumps. That seems okay. And then we have a bump and a bump that are being added, and they overlap in this region, giving me double the height. So we should get something that looks like that when you add those two bumps that are offset just a little bit, okay? Superposition. This is not a terribly good example, but I hope it, I don't know, it gets the idea across. Yes? Amplitude is the same thing that we're calling displacement. Is one of the bumps larger? If one was larger than the other, you still just add them with the size that's there. So if this bump was this big, then I would have this here. It does, yeah. Yeah. Anyone else? Okay, so let's treat this mathematically just a little bit. We're still looking at this phase relationship thing and constructive and destructive interference. Notice, part A there says they're in phase. The peaks perfectly line up, okay? So when I add them together, I get this thing at the bottom, and yes, I don't know if it's drawn perfectly to scale. Does this thing fit maybe here? I guess that is maybe those two heights added together, roughly speaking at least. Yeah, you're okay with that? Okay. So the two peaks add together, and these two valleys perfectly line up, so I get double the valley depth, all right? So anytime they're in phase, then that's perfectly okay. Now, we also can get in phase if I just shift these by one exact wavelength, okay? So they don't have to start necessarily at the same time, but what if maybe we're creating one wave like this, we're oscillating something up and down, and maybe I create one wave and I go through one exact motion, and then I start another one at the exact same time. So the peaks line up, but it was delayed by one full wave. That will still make them line up perfectly. Or I could wait until this one goes through one complete wave and two complete waves, and then start the second one. They still line up perfectly. They're still in phase. So what we're saying there, as long as they are differing by any integer multiple of their wavelength, we still get an in-phase coherent relationship, and you'll get perfectly constructive interference. So let's see. How are we going to write this? We could say that if delta phi is usually used for phase, if the difference in their phase is equal to 0, or, I wish we had a wave chapter right now, or 1 lambda, or 2 lambda, or 3 lambda, or n lambda, we get constructive interference. And we should specify this is perfectly constructive. The peaks are exactly matching up, and we're getting the greatest possible displacement that we possibly could. So it turns out that I can express this another way as well. I hesitate to do this, but some of the examples are going to do it, and there's really no way to get around it. One wavelength, 1 lambda, is often re-expressed in terms of degrees. So we can say that's the same thing as 360 degrees or 2 pi radians. Since it's an oscillation, it's something that happens and then repeats over and over again, you can relate it back to a circle, because a circle kind of does the same thing, right? You go all the way around, and then you do the same thing again, over and over and over and over again, okay? So when we say that it's gone through one wavelength or one complete oscillation, we can call that 360 degrees or 2 pi radians. If it's half of a full oscillation, well, then everything still applies, 180 degrees or just pi radians. So sometimes we use this degree or radian terminology to indicate how different things are. So I could re-express this relationship as if the difference is 0 or 360 degrees or 720 degrees, or you get the idea. Or we could say 0, 2 pi radians, or 4 pi radians, et cetera, et cetera, et cetera. All mean the exact same thing. So how do we get perfectly destructive interference based on what we've written there so far? Thoughts? Yeah?
So one wavelength has to be pushed over by pi radians.
By pi radians, so by half.
Yeah.
Yeah, let's figure out how to write that. So essentially we could write this as, well, not 0. 0 is not going to work. We could say pi over 2, or lambda over 2. Lambda doesn't work, but 3 lambda over 2 would work, and 5 lambda over 2, and so forth. Agreed? Okay, so we're just going to the halves, and everything is fine. So what can I say about n over here? Any thoughts? Let's write this as, let's just write it as n lambda over 2. And then we could see n is like odd integers. It could be 1, it could be 3, it could be 5, and so forth. Okay? Question back there. If one has a varying amplitude, yeah, that is unrelated. All we care about is where it is in the wave, not how much it's waving. Okay? Yes? Take a look at what's happening above. And let me write this first so that we've got a full record. Okay? So let's see. Constructive interference is happening in this case and over here in this case, where either they perfectly line up or they're shifted by a full wavelength. That would allow them to still line up. If you imagine just taking, say, this bottom wave and just sliding it over until this peak is here, that one goes to right there. I've shifted it one wavelength, and then still everything is going to line up going forward. Okay? However, if I shift it by half, so I don't move this peak all the way to there, but I just move it halfway, then the peak is going to line up with a valley, and they're going to perfectly cancel out. Okay? So that happens whether I'm dealing with just one or a half, but I can also do multiples of that as well, and the same thing will happen. The second case is destructive interference, yeah. Oh, let's draw a different color line and see if I can get that up there. Ooh, there we go. Okay, your question. Which one? Where? C. They don't start at the same time?
But they line up? Start at the same time?
That's what's happening. They just didn't draw that terribly well, I think. It would have been better to maybe leave the blue one out and like make it start there. That would be a better description of that. Yes?
Do we need to focus on like in phase and out of phase as much, or do we need to realize that the two waves are constant, going up and down?
I guess you should recognize the terminology of whether something's in phase or not. If it's in phase, the only way they can be in phase is if they perfectly line up. Everything else is out of phase. Okay, so how does this happen in a more natural way? So not where I'm like manually making waves start at a different time. It's like, let's start this one, and then, whoa, let's bring this one in, and then they add in some sort of weird wave based on how much out of phase they are with each other. What if instead we had two sources of light? And you can see over here at the right side, they describe these as radio antennas. Radio is a type of electromagnetic wave. It could be light. It could be anything that's creating an electromagnetic wave. And they're just sending that off in all directions. Okay? And there is a lot of stuff that's happening here. We're going to focus just on this one point. So there's two sources of light. Let's just write that as, we'll say, sources of light. Two different things that are making light. So maybe one is over at this location and one is over on the other side of the room, if that helps, okay? So can you see it? It's sitting right here. Here is a source of light. It's beaming light all out into the room. It hits you hard, I could tell, all right? All the way over sitting at the sink is another one. Two different sources of light that are being beamed out into the room. And we're worried about point P1, and I'm thinking you get to be point P1. Why not? All right? We're looking at one point in the room where light is coming from those two sources and reaching the same point. At that point, it's going to interfere. That source of light and this source of light, the two waves that hit this point are going to interfere with each other in some fashion. What we don't know is like what part of the wave each of them is in once it gets to that point. Okay? Remember, both of them have to be coherent, meaning whatever their phase relationship is, it has to be constant. Let's just, for the sake of this argument, say that they're in phase. It's like I turned them on at the exact same time, and like imagine in slow motion, they start sending out a wave that's like perfect, like the peaks and the valleys are perfectly together, okay? Also, they're monochromatic. Let's just pretend they're red. The exact same color of red, which means they have the exact same wavelength, okay? Now think about those waves as they leave the two sources of light and begin to travel. Are you ready? This should be a good time, okay? So this one, I turn it on. Let's pretend it starts at a peak, and it's like, you know, it's doing this as it goes through space. It hit him kind of like coming down from a peak just a little bit, okay? That's the amplitude or the displacement of the light wave at that point. What caused it to be at that particular point in the wave when it traveled that distance? Why wasn't it at a different point in the wave? I think I heard the answer. It's all about the distance, right? If we had been worried about this point in the class, well, then it would have been, and maybe it's at a different point in the wave when it gets to here. The distance the light had to travel to get to that point affects what part of the wave it's in when it gets to that point. Now, what about the other source of light? I don't want to do that one. That sounds like too much work and way too much crawling and falling down, all right? But let's just imagine from that other source, it's like, right? It's going up and down, up and down, up and down. It has to travel farther than that light wave did, and it gets to this point, and it's at some point in the wave. We don't know what point, okay? Once it gets here, those two amplitudes, those two displacements are going to add, whether they give us a bigger displacement or a smaller, all depends on what part of the wave it's in at that point. You understand perfectly, don't you? Yeah? Because I'm standing right in front of you. So it's all about how far the two waves had to travel. What if we had gone, say, maybe right here, right in the middle between the two. Let's say they traveled exactly the same distance to this point. They should add perfectly, right? By the time they get here, they're going to be at exactly the same point in the wave. So whatever that is, if it's at the peak, you'd get double the peak. If it's at the valley, you'd get double the valley. If it's like a quarter of the way in between, that thing would add. They would be at exactly the same point in the wave by the time they got here. Agreed? And that's different depending on different points in the classroom. Your question. The wavelength is set, and it's exactly the same at the start for both of them. So, like the wavelength, how long the wave is the same for both. It would be given based on what type of lights we were using. Yeah, because you're right. Like if they're the same, but I picked a different color, right? They're going to be at a different point in the wave here because maybe like the wave is quicker or maybe it's spread out more. The different different colors of light are going to interfere in a different way at a given point. Okay? So notice there on the right, it says there's those two little arrows pointing, saying different path lengths. What type of interference happens and exactly how it interferes all depends on whether they travel the same amount or how much different the length traveled is. Let's write a little note here somewhere. Let's say right here, the difference in the path length traveled. Is there two L's in traveled or one? Or is it either? It's one? You're like, you're an idiot. It's one. I always want two. It looks better with two for some reason. I don't know. Difference in path length traveled by the two sources of light means the waves are in, we'll say, different, it's so out of space, parts of their waving. That makes no sense at all. I'll zoom in there so you can see it a little bit. The difference in the path length traveled by the two sources of light means that those two waves are in different parts of their individual wave or their waving. Nobody talks like that, but hopefully it helps you understand what I'm saying. So we're going to express that mathematically, okay? What if they travel the exact same distance, we know that they're going to be perfectly in phase with each other, right? If the difference in the distance they travel is exactly one wavelength difference, which that's going to be hard to determine, right? Think about the wavelengths of light. It's like nanometers. So it's like either right here or right here. Like that, like we can't. So that's probably not going to happen, that you can detect the difference traveled in distance by one wavelength of light. That seems unlikely. But if it was, they would still perfectly line up, because it would be like this third case. If it was exactly two wavelengths different, or three or four or five or six or seven or however many, you're going to get this first relationship once again. So let's re-express this perfectly constructive relationship one other way based on a difference in path length. So we will say if delta L, the difference in the distance traveled, is equal to, and just to keep things the same, let's call this n lambda, where n is equal to 0, 1, 2, 3, and so 1, 2, 3, and so forth. Any integer multiple of the wavelength, you'll get perfectly constructive interference. Or we could say for the other case, no, not that color. Let's go with this one. If delta L is equal to n minus a half lambda, this will work, where n is once again equal to 1, 2, 3, and so forth. We get half wavelengths in difference. Okay? So that'll give me the half, 1.5, 2.5, 3.5, 4.5, and so forth. So this tells me what has to happen to get constructive or destructive interference perfectly between two waves. This connects it to a distance traveled, and how much difference in that distance we have gives us either constructive or destructive interference. Are we confused? Or you got it, sort of? Maybe. You got a question? Yes.
So is delta L the path length?
It is the path length, yeah. Path lengths. There we go. This slide turned messy. Your question. Not necessarily. If they travel the exact same distance or an integer multiple, they'll be in exactly the same point. So I guess we should modify that just a little bit. Are most likely in a different part of their waving. Because there's only these very specific cases where they'll line up perfectly. Everything else is going to be them being at a slightly different part of the wave. We could say it's mostly not perfectly constructive. Because we have cases where it can be constructive, but it's just two positives adding together. It's not the two peaks adding together. Yeah. Yeah. Okay. So let's slide over. Because I want to get to, where do I want to get to today? Is there time or is there not time? It'd be lovely to talk about this. Actually, let's just talk about this big topic completely qualitatively. How's that sound? That sound okay? Looks like there's going to be a talk today of some type. They want in again, don't they? So the bulk of this chapter deals with this thing called Young's double slit experiment, which is weird, okay? It uses this idea of interference with light to show some really interesting properties of light and of matter as a whole, for that matter. Okay, for that matter. And you can see what's happening here. Let's just look at the experiment as a whole. At the bottom, we take some light, monochromatic light. We send it through basically just a little hole. That's all we mean by a slit. By a slit, it's just maybe a long, extended hole. Okay? Once the light goes through there, you can imagine it leaving the other side of this and sort of traveling out in all directions like so. Some of the light will hit this next part where we've decided to cut two holes, two slits, if you will, okay? Some of the light will hit that, and then what happens on the other side of that is illustrated by this diagram. From each one of these slits, light travels out in all directions. Essentially, what happens with this sort of arrangement is that the light emerging from a slit is as if it's a source of light. In fact, the two slits, it say, will be sources of monochromatic, coherent light. And then that light is going to travel out in all directions back here, but we're going to put a screen so that the light can hit it. Now, if you think about it, this is a lot like what we just did with the classroom and two sources of light. Okay, I've got two sources of light, which is the light coming from these two slits, and then it's going to travel a distance to the screen. But if I'm looking at this point, light to get to this point had to travel one distance from this slit, and it had to travel a different distance from that slit. Okay? And that happens everywhere across the screen. No matter what location I am here, light had to travel two different distances from those two slits to get to a point. Meaning, depending on what that difference in distance is, sometimes I'm going to get the waves adding constructively, and sometimes we're going to get the waves completely destructing each other and canceling out, which you see by this pattern that's there. This isn't a terribly great diagram because of, like, they almost show it like in the middle, like it's like these individual beams that are coming out. Like, that's not what's happening at all. It's more like light is everywhere, and when it gets to this point, you get this pattern of construction and destruction because it's coming from two different sources, okay? So this is the experimental version that sort of quantifies what we were trying to talk about here really broadly and really vaguely. Why do we care? All right? I'm not going to deal with the math now. I just want to weird you out just a little bit if I could. Are you okay with being weirded out in the next 4 minutes? Yeah, you want to be? Your question. Nothing happening here with polarization. Doesn't matter. Doesn't matter. Okay, you ready for the weirdness? Are you sure? I don't think you are. Okay? So here's the math. We're not going to talk about that right now. Here's what it physically looks like. If you did it in the lab, you would see like this pattern of bright and dark regions. The thing that's first of all weird, and I've even denoted here, it gets weird, is that if you don't just like turn the lights on full blast, but like make them really, 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 really dim, like barely light at all, Instead, as you go over time, like this is like after a little bit of time has passed, after a little more time has passed, and after a little more time has passed, they've got like some sort of film there that can sort of register light hitting it. It like builds itself up. It's not like immediately, it's like, boom, interference pattern. It's more like little dots of light hit. And if you give it enough time, all of these dots start to form this interference pattern. Which, if you think about it, is a little bit weird. Because they can do this to the point where they can send one packet of light at a time, which we call a photon. Which is like, okay, like let one photon through, and like there would literally be one dot on this screen, nothing else. And then you can wait like a year and say, let through photon number 2. And it goes and it makes a little dot somewhere else. And you could do this for your entire life. And at the end of it, you would get these lines like this as if all of the photons that you sent over 100 years of time interfered with each other. How can that happen? That's weirdness part 1. We'll talk about it a little more on Friday. Weirdness part 2 is that you can do the exact same thing with electrons. What? Which makes you start to think like electrons, that's like matter. That's like mass, right? Light we think of like, ooh, it's a wave. There's nothing like physically there. You can take electrons and be like, I have an electron gun. And we shoot one electron. Nobody does it like that, I don't think. And it travels toward these 2 slits, somehow makes it through and like hits the screen on the other side. And you can do one electron at a time over long periods of time. And at the end, you get this pattern as if all the electrons throughout your experiment interfered with each other. Let's take it a step further. If you can do one electron, you might think like, maybe I could do this with a molecule. Or maybe I can do this with a more complicated molecule. I looked it up, and I don't know if there's been more research since, but in 2013, someone did this with molecules composed of 810 atoms. That's not small, right? Like each shot is an 810 atom molecule. That's like macroscopic at this point. And you can do that throughout time, and somehow they interfere with each other. Of course, people are going to keep trying. Like, how can we do it with dogs? You know, I mean, like, what's going to happen? Can we send a human toward the 2 slits? And they're like, I choose the left one. And they go through that one and, like, do that over time. Would you get, like, who knows? But it's creepy. And it weirds me out a little bit. And it should give you nightmares. That's enough for today. Monday, I was sort of rushing through a qualitative explanation of the double slit experiment, skipping over a few slides and leaving out a bunch of stuff along the way. So I want to back up to this slide and talk a little bit more about interference, and then we're going to deal with the math that's involved with Young's double slit experiment. And you are going to remember nothing that I said on Monday, right? Do I need to just say it all again? No? You want to hear the minimum amount of words from me, I understand. It's sad. So, this question here. 2 waves that are shown there, they are out of phase by how much? Those 2 waves are out of phase by how much? So I already told you they're not in phase, so let's go ahead and cross that one off. Vote when ready. 1, 2, 3, or 4. We've got lots of nice dotted lines there so you can kind of see where one wave corresponds to another. Looking for votes. I see so many different numbers. You're all confusing me. So keep in mind that one full oscillation can be expressed as a trip around a circle, which would be 360 degrees. So what you need to do is look at how far one of these peaks is off from another peak, or compare corresponding parts of any other part of the wave. Peaks are just kind of easiest. How much is that blue curve shifted to the right from the orange one? How much of an oscillation? A quarter of an oscillation? Yeah, I think I agree with that. And out of 360 degrees, how much is a quarter? It looks a whole lot like 90 degrees. Okay? If we just compare a little bit, notice I'm going to draw in parts of this wave. There is 1/4, another fourth, another fourth, and another fourth. Okay? So you can see that this difference is 1/4 of the complete cycle. We'll call that one complete wave. Questions? You got it? All right, we're a little slow starting out. I think we're all trying to recover from all the questions you asked on Wednesday. Wednesday was busy. Wow. Those of you who were here, I needed to clone myself for a little while, and I couldn't, so I just had to be 4 people at the same time. It was exciting. Let's see. 2 light sources emit waves of 1 meter. We're saying the wavelength is 1 meter. You can see the lambda is kind of hiding out there to the right. I don't know why there's a big space. Which are in phase at the start, and then they travel different distances to get to the place where we're going to examine them. Wave 1 travels 2 meters. Wave 2 travels 3 meters. What can you say about their phase relationship once they get there? Nobody wants to say? Anybody? I see a vote for 3. You think it's 3? Anybody else want to say 3? Why 3? Why are they in phase? Yeah, the difference between the two is exactly 1 wavelength. We could write this as delta L. The path difference is exactly 1 meter, and that is exactly 1 wavelength. So if they start in phase, they're going to end up at the exact same point in their oscillation. Okay? Phase differences. Just really everything we talk about in this chapter and the next centers on this idea of phase differences. If they line up perfectly, you get perfectly constructive interference. If they line up exactly 180 degrees out of phase, you get perfectly destructive interference. And then you've got a wealth of options in between where things could be partially destructive or constructive. Okay? So this Young's double slit experiment. Let me back up a little bit and describe what's happening a little bit, and I'm going to actually add some math to these slides this time. The experiment that we're going to focus on really starts here at this middle slide where we have 2 slits in some sort of barrier that's going to act as 2 coherent in-phase sources of light. If we look at that from the top, essentially what happens is a situation like this. Each one of them acts as a source where light rays spread out in all directions. One thing that I didn't tell you is that this thing has a name. It's known as Huygens principle, Huygen'(S) principle. And that is that each slit acts as a new source. And we'll say light diverges in all directions from that point. Each slit acts as a new source, and light diverges in all directions from that point. And keep in mind, this happens with electromagnetic waves, such as light. It happens with any type of waves. If you had a barrier with a small opening on it, say, near the beach, and waves from the ocean are kind of crashing in, you would see something like this happen on the other side of the small barrier, where instead of exactly what you saw coming in from the ocean, which is kind of like plane waves that are crashing, on the other side you would see sort of a semicircular shape of waves traveling in all directions on the other side of that little barrier. So it doesn't matter what type of wave we're talking about, this principle holds, okay? So if we were to move forward a little bit and just zoom in on the slits, we can look and analyze exactly what the path difference is to any point on the place on the screen where all the light rays are going to end up. So notice we are just going to look at a representative ray from the center of each one of these slits heading some arbitrary direction. You need to imagine that like way over here somewhere by comparison, there is a screen where light rays are going to meet. And these 2 rays are essentially going to, well, they're going to hit the screen somewhere off the top up there, okay? And when they hit the screen, they're either going to be in phase, out of phase, or something in between such that they interfere in some particular way. We are making the assumption that this screen is very far away compared to this distance between the two slits. So in other words, we could say that L, which is the distance to screen, is much, 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 much greater than D, which is the separation of the two slits. If we do that, and even assume that those two rays of light actually go to the same place on the screen, it doesn't look like it here, because you can imagine them like maybe coming together to some point. They're essentially going to be parallel, even if they're not really, if they're going to converge on the same point. At any point, you could say that they're like approaching each other so gradually to get to that same point on the screen that we can say that they're roughly parallel. So based on this, we will make the assumption that the two rays are parallel. Right? This is only valid if the screen is very far away. If this is true, you can look at the geometry there below and see what the distance traveled is for both and how much it differs from one slit to the other. Okay? So notice, if I just draw a line here that connects the two that's perpendicular to them both, the length of this line over to the screen and the length of this line starting at that point over to the screen is exactly the same. The thing is, this ray doesn't start here. It actually starts a little farther back. This one has to travel farther to get to the screen, and that small farther distance is just however long this line is, which, as you can see, is the opposite side from that particular angle. The hypotenuse is the separation between the slits. So this little line here is d sine theta. Got it? Everyone can see that? Okay. So that is my path difference. You can see that they've labeled it right here. The path difference between the two slits getting over to the screen before they interfere with each other is going to be equal to d sine theta. Let me pause for a second and see if you have a problem with any of that. Question? If the screen is as close as I've drawn it, then I can't say that these are parallel and that these form right angles, and I can't simplify this as much to say that d sine theta is the difference. We are assuming they are parallel enough. Okay? In that drawing, yes, they are parallel, because the drawing already assumes that the screen is very far away. If it wasn't far away and I had to, say, put the screen right here, then the light from this point, say, goes to here, and the one from right here to interfere at the same place would have to do that. And those are very not parallel. Okay? As I back the screen up farther and farther, this ray starts to turn like this until with the screen very far away, they're essentially parallel. Yeah, I understand that's a problem, okay? We have to make the assumption that the screen is so far away that this is okay. How about this? This line and this line are really, really close to parallel, but they're not quite. They will essentially at some point intersect with each other. We're making that assumption that they are really, really, really close to parallel only because the screen is very, very, very far away. We just have to make that last little jump and just say, let's just go ahead and say it's parallel. Okay? The truth is that they're not quite. All right? Is there anything there that I need to erase? I think I need to erase a couple of things. Back that up. Back that one up. Ooh, let's get rid of that one. There we go. I think we're back where we started with that. Okay? So the path difference is defined by d sine theta here. If you go back a few slides, back to this mess, somewhere on here we defined how path difference relates to the wavelength and the interference. And you can see that that's happening like over, let's change it to the pointer, over here in this region. We're going to use this exact same information because it still applies. We still have two rays of light that are traveling different distances. Now we're connecting that path difference to to this physical thing that we call the double slit, okay? So I'm going to use that exact same information over here to write an equation connecting this path difference to this experiment, and it's going to look something like this. So first of all, delta L, we just determined is going to be equal to d sine theta. And if this is equal to some integer multiple, I'm going to use m this time just to agree with my notes here so I don't get confused. Some integer multiple of the wavelength, then we're going to get what type of interference? This would give me constructive interference. And let's specify that m is equal to, if it's 0, that means they traveled the exact same distance, so they're going to be right in phase with each other. Or this could be 1 or 2 or 3 and so forth. And allow me to put a little other notation here. I'll explain it on the next slide. We can actually say that these are plus or minus 1, plus or minus 2, plus or minus 3, and so forth. At this point, if you just want to stick with all pluses in your head because that's what makes sense, just go with that. I'll show you what the negatives mean on the next slide. So as long as we have integer multiples of the wavelength of the path difference, we get constructive interference. If the difference is like off by a half a wavelength, so if I have half wavelength multiples, then we're going to get destructive interference, and we've already seen how we can write that. So delta L equals d sine theta. Again, that part is for this physical experiment. If this is equal to, what's the best way to write this? Is equal to m plus or minus a half times lambda, we're going to get destructive interference. And this time m is just equal to 1, 2, 3, and so forth. So you can see the plus or minus a half. Do I actually want to write it that way? No, let's not do it that way because I've got it separated out in my notes. Can I delete some stuff? Yeah, okay. It would how much? The whole thing. Let's get rid of it all. It's going to be a little clearer if I separate this into two parts. Okay, let's write this like this. Let's say this is equal to m minus a half times lambda, where m is equal to 1, 2, 3, all positive numbers. And this is on one side of the interference pattern. And we could say this is also equal to m plus a half. I'm confusing myself here. Times lambda, where m is equal to negative 1, negative 2, negative 3, and so forth on the other side of the interference pattern. And I did a terrible job of spelling interference both times I wrote it. Just deal with it. It'll be fine. Your brain will correct it and fill in the letters, move them around where they need to be. You'll understand what the word is. That one side of the interference pattern and the other side connects to this whole plus or minus thing, and I can't show you what that means until we get to the next slide. All of these, though, are for destructive interference. We need them to be 180 degrees or half a wavelength out of phase. Let me add one thing to this slide, a simplification for these particular equations. Let's see. Oh, that simplification involves stuff that's on the next slide. So let's just copy that over. I'm doing just a terrible job at everything today. I'm sorry. It's Friday, and it feels like Friday. So I'm going to copy this over here. There we go. Simplification for these equations, because it is going to use this little diagram right there. Okay? Notice the geometry here at the bottom. They show the two slits, and then they're showing the screen over here somewhere, and looking at a line that goes straight in between the slits over perpendicular to the screen. and just one ray of light that's traveling out to some point on the screen. L, we've already determined, is the distance from the two slits over to the screen. And we've got this angle theta between straight on and over to some point on the screen, okay? Take a look at what's happening there. We can also define y as a distance from the center. Notice it's right behind the two slits out to some point on the screen, okay? So we've got all these different symbols that kind of define different parts of the experiment. We can use some trig functions, and we can say, first of all, that the sine of theta, according to this, is going to be y over the hypotenuse. And if theta is small, you could say that the hypotenuse is essentially the same length as L. In all of these cases, I know all of you hate the trig and geometry that we're doing here, but imagine the hypotenuse and that straight line. If this is a really, really tiny angle, and it's going to be, because remember the screen is very far away by comparison, notice, tiny angle, my arms are essentially the same length, at least I think they are. Like, I don't know what's happening here, right? The hypotenuse and the straight line are essentially the same length, okay? So we can simplify these equations by just saying that L is approximately equal to the hypotenuse. And this is going to allow me to get rid of the sine theta in the equations and simplify our calculations quite a bit. So I could say that sine theta is just equal to y over L. And you can use that in the earlier equations if you just need to get an approximate answer, which will be pretty good for most of our cases. Yes? Why is tan theta equal to sine theta? For the exact same reason. If we say that L is essentially the same length as the hypotenuse, then whether I take the opposite side over the adjacent or the opposite side over the hypotenuse, it's essentially the exact same thing. Okay? Who loves all these little assumptions? No? Do you feel a little bit like a physicist? There's a lot of this that happens in being a physicist. It's like, well, this is a little too complicated for our current abilities, so let's assume it's a little bit like this and we can get an approximate result and everything's good. If you think about it, we've been doing it all along, all the way back to like the first things we did last semester, like air resistance. Let's not worry about that. Let's just throw that out. We'll get answers that are close enough for anything that we're going to do in here. And if you actually had to do actual calculations in a job or something and you need something a little more precise, you'd have to put those complications in, okay? Same kind of ideas are happening here. Now, notice this green, yellow blob here on the left. This is actually what you see on the screen. So if we were to take this entire diagram where we've had a screen that's sort of perpendicular to what you see up there and turn it around so you can see the interference pattern that's happening, you get these bands of bright regions and dark regions, which makes sense, right? Because in some places they're going to be in phase, and in other places they're going to be a little out of phase, and then other places they're going to be perfectly out of phase, and then it'll work its way back to being perfectly in phase again. Yes? How the trig, how which trig? Okay, I'll get there. 1 second more, okay? So that's what it looks like. But if we look at this sort of top on once again, you get this thing over here on the right, okay? Notice they have yellow where we have bright regions, and then kind of that dark gray where we have dark regions. And we can set up the trig and the geometry of the experiment to match what we see on the screen using this. So from the middle, in the middle, we're going to have a bright region. The distance from here out to one of these other ones is what we're calling y. Okay, you can see that on the diagram here at the bottom. That's what connects it to the distance between the two, as well as the separation of the two slits. Okay, don't forget those equations from the previous slide. Remember we had delta L is equal to d sine theta is equal to various things related to lambda for constructive interference. Okay? So this connects to that, and this tells you something about the waves and how they interfere. Notice all of these are given numbers. So if we use m equals 0, we're talking about where they traveled exactly the same distance to get to that middle point. I think that makes sense, right? They traveled through 2 slits, and then they go straight to the middle. They travel exactly the same distance to get there. We call that the one that related to m equals 0 because it's right in the middle. The ones that are on one side, we give them positive numbers. The ones that are on the other side, we give them negative numbers. That's why we had to do all of this mess here with positive and negative versions of everything. Because the interference doesn't just happen from here up. It happens from there down as well because the light rays are spread out in all directions. You feel better now? No? You have a question?
Just need digestion.
Need digestion. Okay, I understand. Big lunch? Yeah. Yeah, I know. That was ridiculous. Okay? So all of this will allow you to calculate various parts of the experiment. Keep in mind, we're making connections to the wavelength of light. Like, how could you ever actually measure a wavelength of light? It's not like you can say, light, stop. I'd like to use my meter stick to see how long your waves are. Like, that's never going to work. But here, we're passing something through a separation of slits that I can measure. Like, that is something I can measure with a meter stick. I can do that. I can measure how far away the screen is. I get an interference pattern, and I can actually maybe use calipers or something to find the separation between a couple of these bright regions. And then I can use these equations to actually find the wavelength of the light that's happening, sort of using an indirect approach. It's like I'm using the interference of the waves to allow me to make a microscopic measurement. And that's kind of cool in a way, right? Your question.
So this is the way to reveal the wavelength of light, so different, like red, blue, green, all of those, you can tell by the
Yes, by making measurements of that pattern.
how would they change?
They would change based on like how spread apart they are, how close are together the gaps, the distance between like corresponding bright regions or dark regions. Okay? And of course, like you could do this backwards. Maybe if I knew the exact wavelength of light I'm using, and I needed to know the distance between 2 holes that are like so close together I can't make the measurement, you could use this backwards to do that as well. Okay? But it's not just practical in those sort of ways. It also did all of this other weird stuff that we talked about a little bit on Monday, which reveals more about like the nature of the universe in a way. Because we have this thing where I can like slow the whole process down and see that different things happen. If I just say, take a laser and shine it at full intensity through this apparatus, it's sort of like immediately, boom, that happens. Okay? But when I start to turn it down more and more, if I turn it down really, really low such that there's not a whole lot of light shining, I have to wait a little while for something like this to sort of build up. It's almost like I'd have to take some film there and sort of collect the light for a little while to allow myself to see it, because maybe at any instant it's just too faint for me to be able to make any of it out. If I slow it down enough, I start to see that light doesn't behave like a wave at all, and starts to act like there's little particles that are traveling through the 2 slits. And over time, you get little dots that appear on your film, and they end up building this interference pattern, which is just in every way weird, okay? I can understand waves. We went into this like assuming light was a wave because we did all that stuff with electricity and magnetism, and then we had EM waves, and we're like, yay, light is a wave, Maxwell's a genius, all of that, remember? You should remember because you were just tested on it, and like all of that stuff should be fresh, unless like you exit the exam room and then you're just like flush, and like all of that goes out and you start afresh. I don't think so. You remember some of that stuff, okay? So we knew it was a wave, so we expected interference because that's the way waves behave, and we expected that totally. The thing that doesn't make any sense is when you look back at this apparatus and you imagine like a bunch of waves hitting this. Like, I can sort of imagine that, like, parts of the wave go through one and maybe parts of the wave go through the other, and then it all just ends up in this big jumbled mess where you add up all the waves with superposition and you get some interference in different places. It's like, okay, I can sort of see that happening. But this idea that we get an interference pattern when instead light starts to act like this. It's like, oh, there's a little dot, and it gets here and goes, there's 2 holes. I want to get to the screen. How do I get there? And it's like, well, I don't know. I'm heading right at this barrier. It's not like I can go and choose the left hole, right? If it's actually a physical little dot that ended up on the screen, you would imagine that like it would go and hit the barrier if it was aimed at it. And if it was aimed at the hole, it would go through the hole and just go straight. And if it was aimed at the other hole, it would go through the hole and just go straight. So you really wouldn't expect this at all. Instead, you might expect over on the screen that you end up with a really bright place here and a really bright place right there directly behind the 2 holes. That's the only thing that sort of logically makes sense. If I were to just take, I don't know, a bunch of baseballs and there were 2 holes over there and I just start throwing baseballs at the 2 holes, most of the balls that pass through the holes are just going to land right behind the 2 holes and the other ones will just bounce off. This idea that it's almost like the photon gets there and says, okay, I'm going to turn into a wave for a little moment, and I'm going to think about like all of the other light that came before me and all the light that's going to come after me, and I'm going to be like, let's interfere, guys. And then I need to take my position on the little screen at this point to give the pattern that's going to reveal itself in the future. That makes little to no sense at all. Agreed? It's almost like all of a sudden time is completely backwards and upside down and nothing adds up anymore. Maybe a term you've heard before, the wave-particle duality of light. This is what is revealed by this whole process. It depends on exactly how we do the experiment. Do we do it quickly, all at once? Or do we do it a little bit at a time? Light decides, like, in one case, I'm going to be very wavy. And in another case, I'm going to be very particle-y. But if you wait long enough, I will reveal to yourself that I'm wavy. It's almost like it's both and neither all at the same time. And that makes no sense. Yes? If you change the intensity to very low amounts, such that only a little bit of light is getting through there at a time. Yeah. Anybody else? Yeah. Could it be particles traveling in a wave? What are they like? Ooh, like they're surfing or something. Particles traveling on a wave. Would that satisfy all the little problems here? Especially the problem of where I just let the thing happen over a very, very long period of time. Even there, it's creating an interference pattern as if all of it happened at once. And that doesn't seem to fit. It's odd. If you want to ask questions about why, I don't have answers. It's one of those things in life that's just not black and white. And as humans, we want answers. It's like the answer is 3. End of story. You have to be okay here with it being kind of in the gray area, and it's like all of the answers are simultaneously true a little bit. And it's only by understanding that all of the answers here are true a little bit that the whole thing is sort of officially true. I don't know if I'm saying anything that makes sense at all, but hopefully you understand something about it, okay? Let me just mention, like I did on Monday, this works with actual mass particles as well. Electrons, it's almost like we're doing the thing exactly backwards. We're starting with something that we already assume that it is a piece of mass and a particle, and it would get to this interface and have to go through one or the other, but it can't be a wave and do both and all of this sort of stuff. And we see the process happen over time. If we just give it long enough, it builds up this interference pattern once again. And that's weird. Okay, we're going to see, I think, it's a little bit undetermined at this point which chapters and stuff we're going to be able to fit in the coming weeks. If we have time, we'll study the fact that mass and things we think of as particles also exist as waves, like we see here, and that all mass actually has a wavelength as well. You have a wavelength. Yeah, it just turns out that the wavelength that you have is really, 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 really small. Okay? It's so small that it really doesn't matter. But it does kind of start to make you wonder, like if we took 80 million of one of you and threw you at a bunch of holes, why would we do that? We're not going to do that. Don't worry about it. What would happen? Who knows? Let's see. Let's leave this for now. We're going to revisit some weird stuff a little bit later and just answer a couple of questions. In a double slit experiment, when the wavelength of the light is increased, what's going to happen to the interference pattern? And all those little wavy lines there are trying to tell you that when you see peaks, like these are the bright spots and the valleys are the dark spots, okay? What's going to happen to the interference pattern if I use a higher wavelength of light? I'll let you think for a second, and I'll put equation on screen. Thoughts? Want to vote? I saw one vote. That was good. Lambda's going up. And m is just a series of integers, essentially, so that's going to stay like it is. So this is going to stay the same, and this is going to be the same, and this whole series is going to be the same. It's this thing that defines like what angle it is out to all of those individual bright regions, okay? So if I want the relationships to stay the same, I need that whole thing to go up as well. Well, that's going to result in a spreading out of the pattern. It's going to be bigger angles out to each of those bright regions, okay? Let's do one more of these. Number one. Things are missing on this. Don't you agree? Were those missing on the last one? Stuff is supposed to be there that you can't really see, but you get the idea. You can understand from the words. If the slits are moved farther apart without changing the wavelength, what happens to the interference pattern? Agreed? Looks good. This time we have an inverse relationship because both of the quantities are on the same side. So if I move the slits farther apart by increasing d, we're going to have a shrinking of, not shrinks together all the way. I don't really like the wording there, but it's going to end up being a little bit more dense. Okay? And then finally, last slide in part A of chapter 3. I did post a 3B. Hopefully you noticed that we may or may not jump into here in a second. I'm going to give you a second to think about this one. Somebody got flowers. Or they stole flowers from somewhere. It's yours? Yeah? Did you just find flowers on campus and just cook them? No? Okay. Why would I accuse you of that? That's ridiculous. I know you didn't do that. So notice we can number these individual peaks, starting with the central one. Corresponds to m equals 0, and then 1, 2, 3, and then we're at like 3.5, okay? Going back to the equation, that indicates that the delta L is something more than 3 wavelengths. It's actually a 3.5 wavelength difference to give us that particular interference pattern, okay? Let's see. Let's get the equation up there once again. So delta L equals d sine theta equals m lambda, okay? So we can just get rid of this middle part. We're looking at the path difference is equal to m lambda. For the third one, m would be equal to 3. So the delta L corresponds to a 3 wavelength difference. Since we're dealing with the destructive point just after that, that would be the point where m is equal to 3.5 officially. But we don't have that as an answer. It just says more than 3 wavelengths. And then that next little peak down there would correspond to 4 wavelengths for our delta L. Okay? Let's see. That is the end of 3A. Does anyone want to throw in a last-second question? Yes. Start counting at the peak. Go back a few slides, and we can see here the one that's right in the middle is the one that we arbitrarily number the 0 point, and then we count positive and negative increasing integers to both sides. Yeah. Yep. Okay. Anyone else? All right. So here's where we stand. There's a couple of topics left in Chapter 3 that I've added in. Thin film interference, we're mostly just going to deal with. I'm going to give you a little bit of quantitative stuff, but largely it's going to be qualitative. And then we're going to talk a little bit about the Michelson interferometer with this guy right here that just has fantastic hair, don't you think? Look at this. I don't know if he's one of the people we had before in these slides. You don't think so? But they just keep inventing new faces, don't they, or different backs of the head. This is actually not on the syllabus. The syllabus says we're skipping this section, but for reasons that I have, I just want to tell you a little bit about it, okay? So I don't expect you to know anything quantitative about this at all. I don't know what you said. I'm just making this stuff up. All right. Thin film interference. For thin film interference, we're going to cover the basics. There will be no deep, in-depth problems that we do with this. I just want you to take what we've learned so far about interference effects with light, and we can kind of put a few of these things together to help us understand an effect that probably all of us have seen at some point, whether it be just out and about, or maybe even in the lab sometimes if you work in a research lab or have at any point in the past, or will in the future. Something like what you see here, where we have soap bubbles. And often if you look at soap bubbles in any type of light and you look at it from different angles, you kind of get this rainbow sort of effect that occurs on the films of the soap bubbles. And we can explain that by means of interference effects. If light bouncing off the soap bubbles was not a wave, you wouldn't see stuff like this at all, okay? Also, if you were to go forward a couple of slides, slides, look at here, slides, microscope slides, maybe if you've ever had 2 of them pushed together all the way, and then as you peel them apart, perhaps, you see sort of these rainbow effects as well. You're seeing interference effects once again, especially if you look in this region. You can see it starts to look like some of the stuff we were looking at the end of last week, these bands of bright and dark regions, okay? All of this can be explained using thin film interference. So let me show you how this works. First of all, we should probably define a thin film. And let me pull up the notes I'm actually using today. There we go. We will say that for a thin film, the thickness is less than, and this is not precise, a few wavelengths of whatever light is passing through it. So thin is thin. A few wavelengths of light in thickness. If we were to talk specifically about something like a soap bubble, what you really have is air on top, and then some soapy water, if you want to think about it that way. The thin film is soapy water, so it might as well just be water, okay? And then inside the bubble, air once again. So it's the soap bubble thickness, which is what we're talking about, and it's incredibly thin. So if we were to represent this over here, we're talking about the index of refraction on the top being that of air, the index of refraction in the middle being that of water, and then N3 is once again air. Okay? Air, water, air. Soap mixed in with water doesn't change the index of refraction significantly enough for us to discuss it. So, the first effect that happens because there are two partial reflections. And you can see that diagrammed here. So the light that reaches the eye with pink eye, apparently, the first one bounces off this interface and goes directly to the eye. But simultaneously, some of that beam passes into the water and then bounces off the second interface back to air, which you can see then will eventually refract back into the air such that I have these two representative beams that reach the eye. Those two beams did not travel the same distance, right? Beam 1 there just had a short path down and back off. Beam 2, however, had to go down to the bottom surface of the water, back up, and then back to the eye. So this length inside here represents the difference in the distance traveled by the two beams. And as we learned last week, when they travel a different distance to reach the destination, well, you can have interference effects depending on whether they're in phase, out of phase, or how much out of phase they are, okay? So we have a difference in distance traveled. So let's write that down first of all. There's a delta L, difference in path length, due to two partial reflections. Also notice we're kind of talking about this a different way than last week. Last week we were putting light through things and then it would hit a screen and we can look at the interference effects. Here it's our eye that's actually the screen in a way. We're seeing the interference effects not because it's an image that's on some other screen, but because the light is actually interfering when it hits our retina. It's in or out of phase when it hits the back of our eye, okay? So we're seeing the interference effects as opposed to them being projected on something else. So that's the first thing we have to consider. I have to add to this, though, just a little bit. There is something else that happens that we don't know about yet, which we would have if we had full chapters on waves in this course, which for whatever reason we don't. And I'm thinking maybe things should be changed. I'm going to start a revolution. I'm changing the syllabus next semester. Now, it's not much of a revolution, is it? That's sad. Sad, depressing revolution. Let's see. And this is this fact. There is a phase change on reflection. When light reflects from a surface, it's possible for it to be shifted as far as where it is in its oscillation. If we had done a chapter on waves, we would have done something like this. We would have talked about starting with waves like in a rope, because that's something we can easily observe and understand. And maybe we would imagine something like tying a rope all the way to that wall, and then I hold the rope over here kind of tight, and then maybe shake the end of the rope upside down. Upside down? That don't make any sense. Shake it up and down to create waves and oscillations in the rope. One thing we might have done also is just maybe create one oscillation. So maybe I'd lift the rope up and go like that. And you can imagine that's going to create like a bump in the rope. You've seen this before, right? And that bump's going to go. You see the invisible rope? Isn't this fun? It's like virtual demos, right? The bump goes like this. There's no bumps behind it because I didn't keep shaking the rope up and down. And it would hit this wall. And when it hits the wall, it would do something like this. The bump would go and invert itself and come back underneath the rope, at least part way, okay? It would be inverted. How much has the wave been inverted when it hit the wall? If it went from being this to going like that, how much? 180? 180 sounds good. 180, half a wavelength, right? It went from being a peak to being a valley. So it's been phase changed on reflection. This happens with all types of waves, not just physical waves in a rope, but light waves, when they hit certain substances, can have a phase change, okay? Let's see. I should add a couple of rules to this. Let's say if it is reflecting off an interface to higher index of refraction, meaning it's trying to go into something with higher index of refraction, something that's denser, something that's thicker is a good way of thinking about that. When I'm talking about the rope in the wall, we're going from string to building, So from the standpoint of the wave on the rope, it's much, much harder for it to wave the building than it is for the wave to wave the rope up and down, okay? It's difficult for the wave to pass into the building. That's analogous to what's happening here. If it's trying to get into a material with higher index of refraction, you get the exact same inversion. There is a phase change of 180 degrees, or the wavelength over 2, half of a wavelength. And another way of thinking about that is just that it's inverted. If it's a peak, it gets flipped to a valley. So when it bounces back, it's 180 degrees out of phase. On the other hand, if it is reflecting off an interface to lower index of refraction, there is no phase change. It just bounces off just like it is. That peak in the rope would come back as a peak in the rope, okay? A way that I can illustrate that is if the other end of the rope wasn't tied to the wall. So once the wave gets to the end, it's not trying to, say, lift the wall up and make it oscillate. Maybe if it's just like lying on the ground. And if I did the same thing and made a big peak in the peak in the wave would get to the other end, and then it would come back part way as a peak in the wave again. Okay? It's almost like when the rope drops at the other end, it like kind of does exactly what I did to this end, right? Lift it up and go back down. The thing goes down there and goes whoop, boom, and then goes back the other way. This is what waves and ropes look like, apparently. I don't know why. You get the idea. Okay? You got the rules? Yes. So in this case, that leads to the next thing we're going to talk about. So let's do that, okay? We have the waves and what happens here. So we still have N1, N2, and now they've relabeled it N1 to indicate that we're going back into air. So we can say that N2 is greater than N1. So that first reflection, it's trying to go from air into something that has a higher index of refraction. That will cause inversion. Okay, the thing that it's trying to get into, not what it's currently inside of. So at this interface, the wave is bouncing off of N2, which has a higher index of refraction. So you can see it gets flipped upside down. Okay, so it's inverted once it reflects. It's shifted 180 degrees out of phase. On the other hand, here at the bottom, it's trying to go from higher index of refraction into lower. So when it bounces, it doesn't get inverted, all right? So we have to consider both of these effects at the same time. If we go back to this previous slide, we have to consider both of these when trying to determine whether the two rays are in phase or out of phase when they hit our eye. Yeah. So it's like an extra level of difficulty from what we've done before. So let's do this for starters. Let's just talk about let's say if there was no phase change. So if we didn't have to think about part 2. In other words, we're just going to isolate the delta L, the difference in the path length first, and then we're going to worry about the rest of it in just a bit. Let me move this down here out of the way. If there is no phase change, essentially the rules are just like what we had before. If the delta L is equal to m lambda, integer multiples. So if they travel exactly the same distance, if m is equal to 0, or if it's 1, 2, 3, 4, 5, 6, 7, whatever, then you're going to have what type of interference? That's constructive, okay? If delta L is equal to m lambda, where m is equal to 0, 1, 2, and so forth, this gives us constructive interference. And just like before, if delta L is equal to some half wavelength, and express that sort of however you want to, let's say, let's just write it as m plus 1/2 lambda, and then we'll again let m be equal to 0, 1, 2, and so forth. we get destructive interference. And I'm talking about totally constructive and totally destructive. These are the ideal cases when they perfectly line up either in phase or perfectly out of phase. I just hate to write the word perfectly or totally every single time we write constructive and destructive. Okay? So this is exactly like what we talked about last week. If we didn't have to contend with the phase change as well, this would be true. So what changes about this if there is the phase change for one of the reflections? They switch. Exactly. If there is a phase change, these flip. The first rule will apply to destructive interference, and the second rule will apply to constructive interference. So if it helps at all, let's think about an ideal case. What if the film is really, really thin? So it's not a thin film, it's a thin film. It's approaching zero. There's almost nothing there at all. So much so that we're not even going to consider a path difference. Basically, they travel the exact same distance to the eye. What would happen? Would you get constructive or destructive interference? Thoughts? Let's write this down here somewhere. If thickness approaches zero. So we're looking at a case where maybe the thin film is like this thick, so that this like refracts and does a thing, and then it's like, oh, the difference in path traveled is essentially negligible. Are those two waves in phase or out of phase? I know you can do this. Either that or you just don't want to tell me, and you've already figured it out. In phase or out of phase? Which one is it? Who says in phase? Who says out of phase? About the same. Good job. Okay? That's nice. So, let's see. The first wave. The first wave we know is going to get inverted. It's going to get flipped 180 degrees because it's just bouncing off the top and going to the eye. So we already know that it's been flipped. The one that goes down that tiny little extra distance and goes back up hasn't been flipped, and it hasn't traveled any difference in length, right? So it's still in the original state of the incoming wave. So if this is the case, we could say delta L is essentially zero, and one of the waves is inverted. Who says constructive? Who says destructive? Starting to lean toward destructive now. Yeah. So if the path length here is equal to zero, they've traveled the exact same distance, it's destructive. Well, that also agrees with this thing at the top. When I have m equal to zero, that's when the path length is equal to zero. Okay? And notice, now we have destructive in that particular case. That should help you understand that these two things have now been flipped when I'm dealing with a phase change. Yes? It's not inverted at the bottom because it's trying to go from higher to lower index of refraction as it tries to pass from water back out into air. Okay? Yeah?
There's no phase change just because the thickness is very, very thin?
There's no phase change due to difference in distance traveled because it's very, very thin. There's still a phase change for the first wave because it's being reflected and not for the second one because it's not being reflected off the top surface. Say that again?
Yeah.
Okay. Remember, we're considering two different effects. If they travel a different distance, they might be in phase or out of phase. If one reflects from a surface where it's trying to get into a higher index of refraction, it always flips 180 degrees. So the fact that I made it thinner doesn't change the fact that one of the rays has been flipped 180 degrees and one hasn't. But added to that, I'm not having to do anything related to them traveling a different distance, which just means I have one that's the original wave and one that's 180 degrees off, they're exactly out of phase. That's destructive interference. But weirdly enough, that seems to be one of our cases at the top that would have previously been constructive interference. So now we're starting to see that the constructive rules apply to the destructive cases and vice versa. Okay? This is about all that I want you to take away from this. If you can get this one slide and understand how to put these together, you're good. Yeah.
So when you say, like, if there's phase change, you're referring to, like, one of the rays has to have phase change?
Yes.
Okay.
Yeah.
Then you consider that flipped.
You consider those rules flipped if one of the two rays has a phase change of 180 degrees. Yes. Anybody else? Okay, let's see. Is there anything else that I wanted to add to this? I got everything but one little side note. One little side note. Notice, for all of these path differences here, we're worried about the wave that's in this material. Okay? This is not considering the wave when it's in the air at any point. The path difference is all about that second wave and did it travel further when it's in the water. Okay? Which means that lambda is going to be different. Remember, the speed of light goes a little slower when it's in something with a higher index of refraction. That means I have to make an adjustment to lambda. So just to make sure you are aware of this, let's derive it really quickly. Let's see. Remember that N is equal to C over V. And this C is the speed of light in a vacuum. And this is the speed in the material. Whatever that material happens to be. N is equal to C over V. And you may remember also that we have an equation for V. Anybody? Something times something. Lambda F. V is lambda F. So let's rewrite this as N is equal to C lambda F. And keep in mind that lambda and that F are both in the material that we're considering, where it's slowed down some. So we should put some type of subscript on those, don't you think? Any ideas? Let's just put a 2 on it to connect with N2 over there on the left. So this is the lambda, or the wavelength, in number 2, and this is the frequency in number 2. And then let's solve this for lambda 2. The wavelength is going to change when it's in that material. So lambda 2 is going to be C over N frequency 2. And then finally, this thing gives me the original lambda, whatever it was before. So this is equal to the original lambda over N. So if I wanted to call that 1 for whatever it was in the air, you can see that lambda is changed by just being divided by the index of refraction of the new material. So lambda 1 divided by N2 gives me lambda 2. Yeah. Got that? Requires maybe a little leap in there because we didn't deal with a wave chapter. And again, I'm a little mad about that. Revolution. No, forget me. It doesn't matter. Just keep in mind that you can't use the vacuum wavelength. You have to use the wavelength for that particular material. All right? Let's see. This next slide, I don't think there was anything here other to say than, oh, look, slides. Like, you can see this effect here. They've got all the rays drawn out as far as what's happening. It goes from air to glass to air to glass. It's a little more complicated through the reflection. I don't need you to know anything quantitative about that. So let's just leave that and go to the last thing. And this is a section of the chapter which is not on your syllabus. But I think it's important at least to discuss qualitatively what's happening with what's known as the Michelson interferometer. And the reason for this is because of this. You saw this image last week? Yeah, black holes, yay. Wasn't everybody excited on Wednesday? Like scientists, non-scientists, students, faculty, everyone's just like smiling because it's like, oh, hey, look, we see a black hole. That's fantastic. But maybe you didn't get a feel for how big the black hole was, so that's why I'm showing this one. Notice inside here. This is our sun in the orbit of Pluto sitting inside the black hole itself, inside the event horizon, and Voyager 1 sitting out there, which is like the farthest we've had any probe go from our solar system. That's just depressing in a way, don't you think? Big black hole. Where would the Earth's orbit be in this diagram? I don't even think it would make it outside of those little rays that are coming off the sun, because Pluto is way out there compared to the orbits of the inner planets. So, I mean, just really, really tight around the sun would be the orbit of the Earth. So, black hole, big black hole. Yes? Depressingly large. Hopefully we've got another image coming soon from the black hole, the center of our galaxy, as opposed to a galaxy 50 million light years away. But it's a much smaller black hole, but it's much closer. So we're probably going to get an image that's kind of similar. Okay, it's not like it's going to be an ultra high resolution or something because it's in our galaxy. But it's ours, right? It's our black hole because it's in our galaxy. And we should feel a little more attached to it. I don't think we want to do that. No. So keep this in your mind. Black holes. Regions where the gravity is so strong that everything is really, really screwy. Light can't even get out of the black hole. If it gets too close, light gets sucked in. All is terrible. If you look really close at this, you can even see like the little aliens that are getting dragged into the black hole, and they're like really stretched. No, you can't. Just ignore me completely, okay? Keep that in your mind because I'm going to talk about the Michelson interferometer, and you can see 2 slides in the future. Hey, black hole comes up again, okay? So there's a connection here. Just bear with me for a second, all right? The Michelson interferometer is something that uses the wave nature of light and the fact that we can use these interference effects and sort of magnify the wave nature of light to measure really, really, really tiny distance changes, okay? So let me take you through it, ignoring part of this diagram because you don't really need all of it. Let's look at the one over here on the right, and let's get rid of this. And let's get rid of this, okay? So they're just extra details that explain some aspects of the experiment that we don't need to know to get the basics, okay? So notice there's a laser, and in the middle, you can think of this as sort of like a, let's call it a semi-mirror. Light both reflects from it and also passes through it, okay? So it's sort of partially reflective. And let's trace some of these light rays. Essentially what's going to happen is this beam gets to this point and splits. There's going to be a reflection that goes off this direction, and then essentially that same ray is going to pass right back through and make it to your eye or your screen or whatever happens to be there. This is kind of a bad image because I'm pretty sure you're never supposed to put your eye right in front of a laser beam. And yet, there it is. That's exactly what's happening, okay? So let's pretend there's a screen there or something instead. Simultaneously, from this direction, some of this original beam passes right through, goes over to this mirror, and comes back, and then reflects and rejoins that original reflection, and both of them get to the eye or the screen at this point. So we're building an experiment where we're forcing the light to go 2 different directions where it travels 2 different distances. And remember, when I have a difference in the distance traveled, well, they could be out of phase, in phase, who knows what's going to happen, okay? So that means when I put my screen in this location and look at those 2 light waves combining, it all depends on how much the difference in distance is. So D1 is the distance from the mirror, or excuse me, from the semi-mirror out to the first mirror, and D2 is this distance over here. If those are exactly the same distance, well, then the 2 rays traveled exactly the same distance to get to the screen. They're going to be in phase. If it just so happens that one of these mirrors is like moved back just like a half wavelength of light, a half wavelength back means it would have to cover that little distance twice, which means they would be exactly 1 wavelength apart, which means they would still be perfectly in phase, right? If this thing is moved back just a quarter of a wavelength, and we're talking tiny distances now, right? A quarter of a wavelength of light, visible light sits, like, depending on the color, around 500 nanometers. we're talking like 150 nanometers at this point. Like we're talking tiny, tiny differences. If this thing is moved just a quarter of a wavelength, then you're going to get destructive interference, and you can see those changes, okay? So just imagine we're just talking about the beam right in the center. This is the full pattern if you kind of look at everything that's happening. And imagine you just watch whether the middle is dark or whether the middle is light. Just by one of these mirrors moving a quarter of a wavelength, the center of this will go from being dark to lit up because it would be in phase once again. So simply by observing this pattern and ideally looking at this with not just your eye and like a little ruler, like that's terrible, right? You use some sort of photo detector so you can actually detect tiny changes in how much the intensity has changed. And all of a sudden you can measure really tiny differences in how much this mirror might have moved. And it's really, really sensitive, okay? So this experiment was built on a large scale, which I'm sure you've heard about the experiments over the last few years coming from LIGO, which is, hold on, let me get it right, the Laser Interferometer Gravitational Wave Observatory. There we go. I said it right, all right? Interferometer. This is the Michelson interferometer sort of writ large. If you look at just this whole structure here, you should see something that kind of looks like this. Can you see the comparison? Maybe? Like notice there's a long way out to one mirror and perpendicular to that, a distance out to another mirror. That's what these things are. All the way out there somewhere is a mirror, and all the way up here somewhere is a mirror, okay? The rest of the experiment and the source laser and the splitting of the beam all happens right here, and this is where the two beams come back together. So they split it, send it a long distance out, they come back, and then they look at the interference pattern, okay? If one of these distances changes a tiny little bit, it changes the interference pattern. Now, of course, there's a lot of different ways one of those distances could change by a quarter of a wavelength of light. One of those might be something like, I don't know, like that, right? Truck rolls by. Well, of course, that's going to vibrate things a little bit. Things are sad. All the physicists down in this building are like, we see, it's a truck. And everything is lost. So all of this has to be incredibly isolated from the environment, put in a remote location. Somehow someone needs to also be looking to see if the ground is vibrating or anything because they want to rule out all the possible sources of a distance change coming from something on the Earth. Is that difficult? Sounds difficult, right? Your question? Because we're looking for even tinier changes in distances than what we could see perhaps if we just let it go from here to here and back. It allows us to sort of magnify even smaller effects by looking over a longer range. Okay? And they see this happen. The thing is, it's weird. Notice these lengths. Here's an actual diagram of the exact same thing, except they give these distances 4 kilometers out to each mirror. So this is a really, really large experiment. There's 2 of these built in 2 locations, which helps them also determine whether something local was happening around one. If they both detect the same thing, then that probably means that it wasn't just a truck rolling by one of them, or it wasn't somebody who sneezed at the end of the tunnel, right? You can isolate these things by having 2 experiments. So 4 kilometers, and what they're looking for is not whether a difference in length that we can observe. What do we mean by that? What we're looking for is, like if I imagine holding these 2 things apart by about, I guess that's a foot-ish, right? Okay? Space in between there. It's possible for that literal space to change its distance. Meaning that there is a fabric that everything is constructed of that perhaps you've heard of called space-time. Like we have an x-coordinate, a y-coordinate, a z-coordinate, and a time coordinate. And everything everywhere has these 4 coordinates. But really, 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 really strong gravitational sources can bend this structure, bend this x, y, z, t structure of space. They illustrate it here in 2 dimensions because it's really hard to think about, right? It's hard for me to imagine like, oh, there's 3-dimensional space here, and if there's gravity, I have mass, I cause gravity, it's possible for this space to get like changed and distorted and warped in some sort of way. It's easier to imagine if you think about it 2-dimensionally and just think of like the whole universe as being a big flat sheet. Then you can think of sources of gravity as sort of sitting on that sheet and making indentions in it. Just keep in mind, this 2-dimensional idea has to be transferred to 3 dimensions, and that all of a sudden just kind of makes your head hurt a little bit. Like, how does 3-dimensional space get indented? It's like, it's like kind of like gets pulled in on itself in all directions somehow in a way that I can't really see. That starts to get a little creepy, all right? Black holes, on the other hand, they are extreme sources of gravity, the largest sources of gravity we know. So they cause extreme indentions in the fabric of space-time, meaning that this 3-dimensional structure of space is bent. Well, what happens if you have black holes that are doing things like, I don't know, colliding with each other, or maybe orbiting each other? You can imagine that this structure of space-time around it could have waves in it, the way they've sort of drawn here with a black hole and a neutron star around it. If it helps, just imagine 2 black holes like running into each other and then ripples going out, because essentially the black holes are doing to the fabric of space what I was talking about doing over here to the end of a rope. Like that's you can see, but ripples in the fabric of space, how can you see that? How can you observe that? How could you ever observe that? Because the fabric of space is completely invisible to us. Where'd the iPad go? The fabric of space took it away. That's what LIGO can detect. If this 4 kilometers changes, light can see it. If it changes even by the tiniest little bit, the interference pattern can change and would be observed, and you can see that change. Let me back up from this just a little bit. This is not, if I had a 4-kilometer-long meter stick, which wouldn't be a meter stick then, if I had a 4-kilometer stick, first of all, I don't know how I would carry that, but you get the idea. Like 4-kilometer stick, here we go. And I like lie it down like right next to this thing, and I'm like, okay, if this thing changes, I'm going to see it. You would never observe it because the meter stick itself, the 4-kilometer stick, is also in the fabric of space that is potentially being changed by a wave passing through. So in other words, like that distance of the tube shrinks just a little bit because a wave passed through. So did the meter stick. If you happen to be standing there, so did you just a little bit. And if everything changes, you can't see that happen. But light can, because it has this wave nature and it's also a constant. Its speed is constant. No matter what space is doing around it, it travels at 3 times 10 to the 8th meters per second in a vacuum. This allows me to sort of like separate myself from this changing space-time world and actually observe the change. And weirdly enough, they see this happen. And that should really creep you out some, right? Like this invisible structure of space is changing in some way that I can't see. As far as I know, a wave just passed through me, and I like lost half my thickness and then expanded again in a way that I could never see or detect. But if we had LIGO sitting next to us, we could be like, something just happened to you. It did? Like, look, the interference pattern changed. And I'd blame it on a truck, and then they'd say, oh, yeah, that's right. And then we would move on with our life, okay? Black holes exist. We see their effects now visually, which is kind of cool, but we can also see them doing things out in space by seeing their effects on space-time by using the Michelson interferometer built really, really big. Awesome stuff. Who's got questions? I don't have any answers for you, but who's got questions? How are we doing on time? We're good. Nice. Yeah? What? Can you break through space-time? What do you mean by breaking through it? Can you break through it? Well, I can't. It's all theoretical. Who knows, right? If this thing at the bottom eventually is just, there's just so much mass, you start to wonder, like, Well, what happens down here? Like, does it eventually just like pop? Who knows? Theories, some people say like, oh, well, everything dies when it goes into a black hole. Some people are like, no, maybe they're wormholes to other places in the universe. And maybe, hold on here.
Not when space-time kind of ends, per se, but it's kind of...
Yeah. What if, like, two places in the universe, like, and you have all this warping by gravity and stuff, and in a way we can't see, maybe the two places are in some other dimension close or nearby? What dimension are we talking about, right? Because, like, how is this bent? It's bent in another physical space that's not X, Y, or Z. So clearly we're kind of talking a little ridiculous here at this point. And then maybe there's like a black hole here that like bends this one a lot, and there's a black hole here that bends this one a lot. Maybe we could get from point A to point B. Theoretical stuff. How could we ever test? Not in our lifetimes, but I don't think you want to be that pilot. Like, another black hole. Let's see if this one goes somewhere. Never heard from him again. Although maybe he's just so far away now. He did, yes. He's cooler than us, I guess. I don't know. That's about all I want to say today. We'll leave it with chapter 3. Enjoy thinking about these things, or not. Goodbye.